Have you ever really stopped to think about a rock, a river, and the air all around you? I mean, they seem totally different, right? One's hard, one flows right through your hands, and the other, well, you can't even see it. But what if I told you that deep down, on a scale you can't even imagine, they're all made of the same basic stuff, playing by the exact same rules? Let's dive in and find out what's really going on. It all kicks off with a really simple question. I mean, look at this. You can stack stones, you can make a pile of sand, no problem. But have you ever tried to pile up water? Of course not. It just flows everywhere. So why is that? This simple, kind of obvious question is actually the key that unlocks the secret nature of pretty much everything. So, to solve this little mystery, we need a clue, and we're going to find it by doing something really basic. We're going to take something that looks whole and just break it apart. All right, so let's start with this. A plain old stick of chalk. It's solid, it holds its shape. To our eyes, it looks like one solid, continuous thing, doesn't it? But, it doesn't take much effort to just snap. Now we have two smaller pieces of chalk. The stuff itself hasn't changed a bit. It's still chalk, it's just in smaller chunks. But why stop there? We can keep going. We can take those pieces and grind them and crush them until we've got a fine powder. And now it seems like we've hit a wall. We can't really break it down anymore with our hands. So, is this as small as it gets? Oh, not even close. If you grab a magnifying glass and take a look, you'll see that powder isn't a single thing at all. It's made up of countless, incredibly tiny little grains. And here's the really wild part. Every single one of those microscopic grains is still 100% chalk. And here's the big reveal. What's true for that chalk is true for everything. The rock, the water, even the air you're breathing right this second. It's all made up of a huge number of ridiculously tiny units that we call particles. Matter isn't smooth and continuous. It's grainy, it's particulate. And that right there is the first massive piece of our puzzle. Okay, so if everything is made of particles, what's the deal? Why is a rock different from water? Well, it all boils down to two very basic rules that control how all these little particles behave. Rule number one is all about space. See, these particles aren't squished together perfectly. There are always little gaps between them. We call these interparticle spaces. And here's a mind bender for you. What's in those spaces? Nothing. Not even air. Just pure, empty space. It's why if you dissolve a spoonful of sugar in water, the water level barely rises. Those little sugar particles are just slipping into the empty spaces that were already there between the water particles. Rule number two is about a force. Think of it like an invisible glue. All these particles are constantly pulling on each other. This is called interparticle attraction, and it's what holds stuff together. Now here's the secret to everything. It's the strength of this attraction that decides whether something is going to be a solid, a liquid, or a gas. And what's really cool is that this isn't some brand new idea. Thousands of years ago, an ancient Indian philosopher named Acharya Kanad said that all matter was made of these tiny, indivisible particles he called parmanu. So this quest to figure out what we're all made of, yeah, it's been going on for a very, very long time. Okay, so now we have our two rules, spaces and attractions. With just these two ideas, we can finally go back and solve our original mystery. Let's see how they perfectly explain the three states of matter. Let's start with solids. Think about those stones from the beginning. They've got a fixed shape, right? A fixed volume, you can pick one up, put it down, and it's still a stone. And if we could zoom in, we'd see its particles are packed in there super, super tight. They aren't really going anywhere. And why is that? Well, in a solid, that invisible glue, that force of attraction, is incredibly powerful. The spaces between the particles are tiny. This super strong attraction locks every particle into a neat, rigid structure. They can't just wander off. The only thing they can really do is just vibrate in place, kind of like they're shivering on a cold day. All right, on to liquids. Like our water, they definitely have a fixed volume. A gallon of water is always a gallon of water, but they have no fixed shape at all. They just flow and take the shape of whatever you pour them into. This tells you their particles are a bit looser with a bit more freedom to move around. So what's happening here is that the attractive forces in a liquid are weaker than in a solid. The particles are still held pretty close to each other, which is why liquids have a fixed volume, but that glue isn't strong enough to lock them down, so they can slip and slide right past one another. And that's exactly what flowing is. And finally, we get to gases, the air.
Now, these guys are the total rebels of the particle world. They have no fixed shape and no fixed volume. Their particles are super far apart from each other, and they just zoom around with complete and total freedom. See, in the gas world, that attractive force we've been talking about is practically non-existent. It's so weak that the particles just don't care about each other. They have so much energy that they fly around freely and randomly, bouncing all over the place and expanding to fill every single nook and cranny of whatever container they're in.
This table right here just sums it all up perfectly. As you go down the list from solid to liquid to gas, just watch what happens. The spacing between particles goes from minimum to maximum, the attraction between them goes from maximum down to basically nothing, and their movement goes from just vibrating to flying all over the place. It's this beautiful, simple relationship between space and attraction that creates the entire physical world we see.
Now, you might be thinking, okay, that's cool science, but what does it actually have to do with real life? Well, it turns out this particle stuff explains basically everything you experience every day.
Ever wondered how you can smell cookies baking from another room? Or how perfume seems to fill a space? That is the behavior of gas particles in real time. Tiny perfume particles escape the bottle as a gas, move freely and randomly through all the air particles, and just spread out until they eventually find their way to you.
Or how about doing laundry? That's literally a tiny particle battle happening in your washing machine. Soap particles are designed so that one end loves to grab onto oily dirt and the other end loves to grab onto water. This little particle team-up literally yanks the stain right off your clothes. It just goes to show that understanding particles helps us solve all sorts of everyday problems.
So let's end this with a final little thought experiment. You're sitting on a chair, right? That chair is made of particles. So what would happen if you could just, poof, magically remove every single particle that makes up that chair? What would be left? The answer is nothing. Absolutely nothing at all. Because here's the biggest takeaway. The particles aren't just in the chair. The particles are the chair. They are the river. They are the air. They are everything.